Professor Coifman.
Thank you. It's a pleasure to be able to sort of tie together a lot of strings, that a lot of topics that we have heard about today and you will hear about tomorrow, into a box that you may have not heard about, which is sort of the outside world of digital databases. Okay? So basically what I would like to show you is that on the one hand, ideas and methods of classical harmonic analysis apply and are very useful to organize, say, point clouds in Rn if you want to talk mathematically, or just take a database like a psychological questionnaire or financial data or medical data for that matter, and do harmonic analysis on it, right? So we have to understand all those terms have to be explained, and I have to give you at least some impressionistic view on how we can achieve that and what it really means to do harmonic analysis in that part of in that context. That's on the application of mathematical ideas to the outside world. What you will see in return is that the intuition from the outside world tells us quite a bit about things that we have been dealing with for many, many years. In particular, there was a problem that has been bothering me, and I'm sure has bothered physicists and many other people for many years, is if you have the eigenvectors of a Laplacian on some manifold, right, or a Laplacian or eigenvectors of some operator, how do you organize the eigenvectors in a dual geometry to the geometry of the manifold? If you have the eigenvectors of Laplacian on the torus, you know that, and the torus is two-dimensional, they're indexed by two integers, k1 and k2, right? And not by the eigenvalues, which are basically useless, right? When you're dealing with a two-dimensional torus, you expect the structure of the eigenvectors to correspond to this two-dimensional structure, the dual structure. And you will see, in fact, that from those ideas of what you do on questionnaires, you find out how do you actually discover the geometry of eigenvectors by looking at the eigenvectors as a questionnaire on the manifold. So in other words, every eigenvector is a function of the manifold. You interrogate each point by evaluating the eigenvector at that particular point. You have a list of eigenvectors, you have a list of responses. Okay. In the application domain, this would be you have a collection of sensors. You'll basically implement the sensor. You get a list of numbers. How do you organize all of that stuff? So that's my goal. And to be a little less boring at some point, I will actually run the software, okay, to show you what happens. So this is basically this talk will be given, but let me just make two comments. About 40 years ago, Eli Stein, on the one hand, extended classical Littlewood-Paley theory and harmonic analysis to the context of symmetric diffusion semigroups, in which the structure of the semigroup and spectral theory enabled one to prove all kinds of theorems on singular integrals, properties of Laplacians, all kinds of things which were real variable kind of questions, which at the time people were worried on, and showed how you could do that. But there was no geometry at all. This was all in martingale space on some very high dimensional space and so on. At the same time, starting with Calderon and then de Guzman and Weiss and myself, we sort of tried to generalize the basic tools of conventional harmonic analysis to contexts which were broader, like we call spaces of homogeneous type. So that were just spaces with a quadrimetric and a measure, and there was some sort of compatibility between the two. And we showed that we could do Littlewood-Paley theory in there rather nicely. In fact, basically wavelet theory, non-orthogonal wavelet theory was done at that time. And the goal was to adapt to all kinds of situations which were not translation invariant, which were really in a different, much more general context. Those two ideas, those two things have completely fused nowadays. when working on discrete data and trying to get it organized. You use semi-groups to do it, and you build geometries, and the analysis on the geometry are merged together. It all comes in one fell swoop. So what I want to show you first is an example. So the first thing is, I would say, is this. In mathematics, so let's return to analysis in mathematics. I have an operator. What harmonic analysts do, you have an operator, say a potential operator, or a singular integral operator, an integral operator of different species. What you want to know is, what does this operator do to functions? So somehow you need to be able to organize the operator relative to the domain of the operator, or to the range of the operator. So in linear algebra, you do it all the time. You have a matrix, you diagonalize the space spanned by the columns, you find an orthogonal basis, you do the same on the space spanned by the rows. This is called the singular value decomposition. It's a standard procedure, you always do it. It's a very nice tool, but not very good in a situation where your data is in high dimension, and where the taking a matrix times the transpose generates an enormous amount of garbage and noise, because you're taking dot products of very long vectors. Most of the components are basically noise, and it starts to hide all the structure in the system. So the goal, in some sense, is this. So one of the goals of what I'm going to tell you is this. I have a matrix, and we'll see various examples coming from mathematics or from nature. And the matrix is given to you. The labels of the rows and the labels of the columns are basically just random labels. So it could have been initially this very nicely structured matrix, and somebody garbled the rows and the columns, and then it became that one. So the first simple question is, how do you go from there back to this structure, right? I'm not saying that this is a simple product structure. This is not a product structure, okay? So the answer, that's the first question. How do I reorganize a matrix so that in some sense it becomes the simplest possible, okay? This is not simple. There's a lot of variability. I want to reorder the columns and reorder the rows so that the outcome that I get out here is as smooth as possible, okay? So in this case, I started with something where smoothness makes sense. In general, smoothness makes no sense, and we have to invent smoothness, and basically invent geometry for which you can do analysis, okay? So it's sort of like saying, I have a collection of points in Rn, let me invent the manifolds that they're on, let me invent the Laplacian and the geometry and the eigenfunctions and all of that stuff on them, if they actually satisfy those conditions. Again, in the real world, sometimes they are in a manifold. Most of the time, it's a lot of pieces of lots of little different things. So here, I'm going to, what you see here, and I'm going to run the software, which is, if I have it. Oh, yeah, I have it. In fact, I have it here. Okay. So here, this is a matrix of 0 1s, okay, which is the outcome, basically a collection of data coming from a psychological questionnaire. This is the so-called Minnesota Multiphasic Personality Index, or inventory, and there are 3,000 people, 3,000 columns. Each person responds to 560 questions. The responses are yes or no. So let's say no is 0 and yes no is white and yes is black, or vice versa. By the way, each question can be formulated in both ways. So whether it's yes or no, there's sort of a random polarity to the questions. But let's ignore that for a second. And so my question is, can I do on this matrix what I did on this particular simple example we had a minute ago? Find a way of reorganizing all the columns and reorganizing all the rows in such a way that the outcome here is going to be as smooth as possible, okay? But you see, smoothness in this case, you have to understand, cannot be smoothness. Once I've done the reshuffle, which I'll do in a second, cannot be relative to the linear smoothness here, or linear. It has to be relative to some higher dimensional geometry. the population could be quite an interesting demographic structure, right? It doesn't have to be a line. Okay. So the fact that this can be done is nice. So let me organize a matrix. That's already. So I've done it. I reorganized the matrix. I've organized it in a multi-scale fashion. You will see Haar functions, and you will see all kinds of things popping out in a minute. Okay. And the Haar functions are used in a very substantial way to measure the smoothness of that system. So let me do this and show you that. Okay, let me put the grid on. Let me select something. So here you see what happened. So I started with a completely unstructured thing. Now I somehow decomposed it into a collection of demographics. So those are the people. Okay, each column is one person. The column is a profile of one person. And I put together people who have similar profile. So this collection of people here are people with a similar profile. And this is a collection of questions that they're being asked, which are somehow related to each other. By the way, whether it's black or white, as I said, it's sort of a random thing because it's how you formulated the question. Okay. So in any case, you expect, if you did a good job, you expected to have a barcode, right? Something that looks like continuous black line or continuous white line. And every time you see a point here, which is not, for example, this one here, does not fit with the rest of the line, this is a response which is not consistent to the response that other people in the same demographic would have given you, and it's not and so you can say, well, here this person lied. Let's say the question was, you like to get up. I mean, you have trouble getting up in the morning, and it's a job interview. You know the answer, right? On the other hand, if it weren't a job interview, you get an honest answer. So that's the point. But in any case, you see that restructuring the data. So all I've done is all I've done is a permutation, which is a very informed geometric permutation, which I'll explain to you, of the columns and the rows, so that I can, in different regions, in different submatrices here, actually have a consistent model of the response space. Okay. And by the way, we got this matrix of 0, 1s. Now I want to interpret things for you, and so we need to introduce some other things. So let me explain the geometry. First of all, the geometry of the population, of the questions here. Let's do that. Okay, so the questions themselves are organized in high-dimensional space. Okay, bear in mind each question has 3,000 respondents. Okay, so a question is a row in this matrix. So it has 3,000 coordinates, which is what every single person did. And what you do is you link together questions which, across the population, if you know the answer to one, you know the answer to the other. Okay, so that provides you a linkage between questions. When you do that, you define a certain geometry that you can embed in Euclidean space, so that the distance in Euclidean space corresponds to sort of affinity, whatever that means, and I'll define it, in a response space. Okay. So here, the various groups here. So this is one image of the questions, and let's pick a group here, and let's see what it was. So I'm a very sociable person. While in trains, buses, etc., I often talk to strangers. I enjoy social gatherings, just to be with people. I enjoy the excitement of a crowd, etc. So you see, this whole folder of questions that was basically extracted without any knowledge, right, corresponds to a topic. So this, in other words, this particular group you can view as a meta question, which is a topical. In other words, if I had the response for this particular group, I will sort of know if the person, the average response in this thing, will tell you whether the person has easy social interactions or not. If I go to another group here, I'm bothered by an upset stomach several times a week. I'm almost never bothered by pains over my heart or my chest. Parts of my body often have a feeling like burning, etc. So you see, the questions all deal with how do you feel, right? I mean, physical well-being, right? And again, this is by actually just looking at the response of the population. So from the point of view of a So this geometry that I have here tells me that if things are close to each other, groups that are close to each other are groups of questions relating with the same topic, the same concept. I extracted the concept just from the data, not from any. This could have been a questionnaire in any language, right? Or in fact, I don't care what the questionnaire is. I can tell you exactly what's the story. So let's do the same thing. The same organization exists for the. This is a population demographic organization. Okay. So every person has a profile. I organize the whole population into a geometry where people who are close to each other in this scatter plot, groups like that, in the Euclidean geometry here, have a corresponding profile, psychological profile. Okay, and we can check. So we can pick one. Let's say I pick this one. This is the extreme group of people who have lots of trouble. So the first, this is a score is given by psychologists. So this is a very high hysteria, depression. For this group, this is a very high hysteria, depression, hypochondria. I don't know what the other things are. Scores. If I pick another group here, it's exactly the opposite, except all the scores are below normal. So the different groups correspond to basically different kind of assessments that you can make on them for those particular list of psychological functions. So basically the goal is, eventually the goal is, you have a collection of functions like depression score. Can I organize the geometry of the population, the demographic of the population in such a way that the function depression score would be smooth in that geometry? So I know that if I have a person coming in, and he's close to other people who have a certain depression score, his score is going to be automatic, right? So the goal of the exercise is always that, to define a geometry where proximity implies smoothness for a very certain classes of functions. So initially the class of functions is just the coordinates. Eventually, when you add in more functions of interest, like various depression scores or hypochondria and so on, they reconfigure the geometry to respond to the corresponding questions. So one or two more images here. Let me look at this is the organization, the tree. So the whole questionnaire here, as you have seen, I've looked at the topic. So a group of questions would be a collection of questions here, for example. I'm a very sociable person, etc. This is what we have seen before. So this is a group we looked at before, and it corresponds to a topic. So each one of them is a meta question, and you can group them into a meta question, and this is everybody else, right? So basically the whole collection of questions is broken up into a folder structure of topics, and the population is broken up into a folder structure of demographics. So you have two trees going on here. You have this tree, so this is a population tree, and this corresponds to the group that we have seen before. That's exactly the group that we have seen before, people who are very stable and quite okay, and maybe this is probably another extreme. No, that's also pretty stable. So, but the point is, the linear presentation here means nothing. Think of, suppose a situation where that I had the unit square in 2 dimensions, I break it up into subsquares of a certain size, and I want to display it in 1 dimension. I need to have a space-filling curve. What you're seeing here is a space-filling curve, which goes from the three-dimensional geometry I showed you, which maps it onto a line. So this is the usual display by people doing gene arrays and so on, is a display like that, but it's garbage. Okay, the geometry is in high dimension. It's not a geometry in 2 dimensions. But in any case, when you have a tree like this, it's a binary tree, you can build a Haar basis, right? How do you build a Haar basis? A tree, this is just taking the space, you have partitioned it into subsets which are disjoint at a small scale. Then your union of some subsets is a bigger subset. This is what the tree represents. So here is a subset, 3 subsets. The union of them is this one. 3 subsets, the union is that one. The union of all of those is that one, and so on. So you get a Haar basis just by orthogonalizing the characteristic functions those 3 characteristic functions to this one. And you orthogonalize those 4 characteristic functions to this one, etc. Right? So it's very easy to get a very simple Haar basis attached to a tree. When you have a tree, you also have a very natural distance between points. You just define the tree distance between points as, if you wish, the level, the lowest level of the tree that they belong to, so that they belong to the same folder. So the point is, there's a metric there, which is a tree metric, which is sitting around. There's an orthogonal basis sitting around here called the Haar metric. When you have a metric, you have a notion of smoothness, right? Holder functions, holder smoothness. When you have a basis like a Haar basis, you can characterize smoothness by the size of the coefficient. So all of this is completely feasible and also useful. So let me get out of the software and return here, and we'll continue the story. So this is what we've just seen. And again, we've just seen that, so let me skip all of this. But you see, basically what happened here is that we have built on the population a tree, and on the questions a tree. This is a different data set, but the point about it is this. When you want to relate 2 people to each other, okay, you can basically look at the profile of responses and just see how many responses, what's the fraction of common responses, right, which is just taking the dot product. Okay, and so you take the dot product. You're counting how many times they had this exactly the same response. That's a good way of measuring whether the profiles are similar or not. Okay, yes and no. It's you say, think of the question as being +1 or -1, right? You would this dot product between them is not going to be that great. If there's a lot of questions where things are noisy, in other words, if one person was lying, right? So it's much better if you want to understand, for example, whether somebody is friendly. It's much better to look at the whole group, the meta question, which we have looked at. How social you are in various contexts. Take the average response to that as a score for friendliness. So in other words, each one of the folders on the question side is by itself a new coordinate of a person. Okay, so you're getting from this matrix a much bigger matrix going down here, where you have all the scores on all the nodes of this particular tree. Similarly, if you want to organize a population better, you may want to take a topical question, right, a score on a topical question, and compare them, and then you organize. So since you have many more coordinates here, you can organize the population better. Once you organize the population better, you can reorganize the people better, and you have to iterate. Okay, this needs to be iterated 5-6 times for it to be stable, to actually extract language. So basically, in our, if you view this as a location contextual demographic, and this is conceptual questions, you have a sort of duality between the two. One of them is a function of the other, right? It doesn't matter whether rows and columns, but this is what's happening here. Here is another example, which is the following. This is a matrix of sine kx, okay, where I garbled the k. I did a permutation, random permutation on the x, and random permutation on the k. Okay, it would seem that you can't do anything, okay, because okay, so I cheated, okay. There are 500 coordinates in x, and there's only 200 frequencies in k, okay. So in the sense that what have I achieved? The point is that any column here, okay, is going to be orthogonal to any other. Any row here is going to be orthogonal to any other row, because you just take the sum is a sum. It doesn't see the order. Okay. So if I want to somehow organize this, I can't. They're all distance of square root of 2 from each other. Okay. Here I oversampled. Okay. The frequencies here are 200, and I oversampled by a factor of 2. So the distance between an x here, if I look at the nearest neighbor to that x, say to this column somewhere here, that's the one that should be next to it, right? because it's not orthogonal. Okay, it will be the x plus a quarter or something, or a half. So the point is, you can organize very easily the x's in a chain. Okay, they're not all at the same distance. Some x's are closer than others. You can organize the geometry of that. Once you have organized the geometry of that, you want to organize the geometry of those, but they're orthogonal, right? But you can organize them, once you organize them on the folders, on the multi-scale structure of that, then they're not orthogonal anymore. In other words, if I look at sine kx on a small set, they're not orthogonal. So I can relate k to k plus 1. Okay, so this issue, what I was describing as I need to iterate in order to reinforce this psychological questionnaire, I need to iterate here in order to be able to organize sine kx, if you wish, in k. In other words, organize the k's. Okay, so that allows me to do what I was telling you before, is that if I really had the matrix of a eigenfunction expansion, okay, which is what this matrix is, for any eigenfunction expansion, okay, if I can organize the spatial hierarchy, which usually is very easy, then I can organize the eigenfunction hierarchy, and I'll get a tree on a geometry on the eigenfunction. So, and in fact, you see the two geometries. One geometry is sort of a circle on the x, and the other geometry is just an interval. Although it's curved here, it's just an interval on the thing. So basically, 2 points here, consecutive points correspond to consecutive k's, and here correspond to consecutive x's in the real world, in the mathematical world. This is garbage, right? This is what came out of it. Here is an issue. So here's another kernel. This is a potential kernel. Here is a Calderon-Zygmunt kernel. Basically, this kind of organization, and I'll get to it, allows you to actually take a matrix or a kernel and understand how the geometry is related to the effects of the kernel on various on various things. And we are also expanding. We actually are converting it into to the appropriate wavelet basis, but that's another story. Okay. Here's another example, which is how you apply this idea to organize an image. So here is an image with two textures, the texture 1, texture 2. And I'm going to interrogate the image, okay, and use exactly the software I've been running on that image and see what happens when we do that. So what is the interrogation process? It's you take, for every point, you will take the, say, a little 11 by 11 square around the point. You look at the Fourier coefficients of the absolute value of the Fourier coefficients of that particular square as a collection of questions, so 121 questions that you're interrogating the pixel by. And then, so you have whatever the number of pixels, you have 121 questions per pixel. You do exactly what is being done there, and there are different scales. I don't know why this is oh, I see. You don't see the color. Okay. That's the projector. I'll tell you about it in a minute. In any case, so there is this level. What is happening here is that there is a blue boundary here. So this is the scale. There is this tree, and this is a level below the top. The level below that has this and a boundary layer between them. And as you can see, there is a green spot right here corresponding to the particular region here, which is more similar to that texture than to this texture. Okay, and I've not done anything, right? Besides the fact that I cheated and decided what's a good questionnaire, okay, with my prior knowledge, I didn't do anything, okay? So if I didn't want to cheat, suppose the data was given, I take the blocks, I don't cheat, I could do just a principal component analysis around each pixel. It'll do the same thing, okay? So I don't need to know about the Fourier transform. The goal here is not to cheat. Knowing about the Fourier transform is knowing something about the world, okay? And the goal here is, can you actually build the language of data as it comes off the sensors without any a priori prejudice, okay? Completely agnostically, you don't care if it's coming from text document, for images, from an operator, whatever, Okay, the analysis is always going to be the same. So here is this. We did it with a science news document. Again, those are the folders. So every document has a collection of words attached to it, and so you can organize the words like questions. And you see that here is a group of words, and that earthquake, California quake, Southern Crust, seismologists. It all pops out very nicely. By the way, it doesn't work too well if you don't iterate. If you just do one stage, or do a hierarchy on the columns, hierarchy on the rows, and don't augment the coordinates, the thing collapses. I mean, it just doesn't work. Just maybe for your amusement, the whole process came about because I had a student who was trying to do automatic translations of the Bible. And it was a total disaster until this process happened. I'll tell you about it later if we have time. It's actually quite interesting. So let me skip that. So basically what I'm returning now to mathematics. Is about 15 minutes. I can tell you a little bit more. So basically we build this partition tree or martingale or whatever you want to call it, or a tree out there of subsets. So you take subsets which are near each other, and then you agglomerate them, and like you have here are individual blobs, and then the blobs are contained in a bigger blob, containing a bigger blob, and you can orthogonalize the characteristic functions of the different blobs to the parent blob, and you get something looking like Haar functions here. I want to relate the Haar functions, and we do this on the rows and the columns. So we have Haar functions on the columns, we have Haar functions on the rows. In other words, we have a basis, which is a tensor product of the two, for the whole matrix that we got. Okay, so I build this based on the matrix, I build this based on the matrix. Now I can take the matrix and ask myself, how good is that matrix in that basis that I built? Okay, and in fact measure very quantitatively how smooth, how successful was I in actually organizing the work. Okay, the whole point is I'm doing this. I mean, fine, it's a nice algorithm, but can I measure anything? And can I tell? How do I know when to stop or to change structures or split it or do whatever it needs to be done? So I'm coming to sort of those Haar functions in the conventional. So think of the conventional Haar basis. If you have a function whose Haar series is absolutely convergent, okay. In some sense, you say that such a function, for any orthogonal basis, if you have a function and the sum of the coefficient is finite, in some sense the coefficient, the function is sparse. And for those of you who you'll hear about maybe compressed sensing or other things, this is standard. But it's very easy to show that if you have a function like a function satisfying this condition, in the case of a Haar basis, in order to approximate the function to some power of epsilon, if you have that condition, you can approximate the function very well to some power of epsilon. With a small number of coefficients, you just have to look at coefficients whose size is larger than epsilon. So that, and so in other words, you can truncate a Haar. So f is a full Haar series, but if you truncate it at r larger than epsilon, this is sort of at a given scale, then you're left with a series like that, and this is just a tautology. It's less than the sum of the coefficient times square root of epsilon. That for Haar functions, this just follows from the fact that they're normalized to have L2 norm equal to 1. They're less than the characteristic function of the support, and normalized by the size of the support to the power of half, because the square has to have integral 1. So just that condition implies that the entropy condition of this L1, little L1 condition, implies that you can approximate the function with a small number of coefficients corresponding to the size of the support. So that's one thing. The other thing that you have about such Haar function, this condition that I wrote here for those of you, and we have seen the talk before, it's a Besov condition. It tells you basically that the function, in the conventional sense, it means the function has half a derivative in a Hardy space. And so the function has to have smoothness, and that's an abstract statement which I'm going to reformulate. When you have a function satisfying this condition, then you can write it as a sum of a good function and a bad function. The good function satisfies the Holder condition relative to a distance, which is defined by the tree, as I discussed before, and the bad function has small support. That's essentially what is called the Calderon-Zygmunt decomposition. Some of you know it, some of you don't, but let me just formulate it in a way that it'll be very simple. If you have a function of whose derivative is in L1, right, then you know that you can write the function as a function which is Lipschitz with constant lambda plus an arrow which has small support. That's the formulation of the classical theorem. If you have, coming back to what I'm doing here, just to explain it on the ground floor, suppose I have a sequence, suppose my matrix to begin with was just a string of numbers, random numbers between, so it's one row and 1,000 values, one row of length 1,000, okay, and all the values are random numbers, okay. How can I make it regular? I'm saying I've done something that made the whole thing regular. The point is that what I've really done is rearrange the values. So now the function that was random is a decreasing function, which has automatically a derivative which is a measure, which means that it's a smooth function. You have seen the rising sun lemma a few minutes ago. And so it's very easy to see that it's really, it's the function that you have is a Holder function plus a function with very small support. But what I'm really saying, this is true for the full matrix that we had, that if you can estimate that, first of all, the measure of success is how many, if you expand the whole database in the geometry of the database, the sum of the coefficient measures how smooth, how successful you were, and it tells you that you were successful in a way that you can predict any coefficient in the database from any collection of, say, 3 neighbors with estimates which is of order 2 as opposed to order 1. Okay, and I'll get to, I don't have really time, but I'm saying this allows us to actually prove that you can have really decent estimation and prediction and so on. Let me return to one example on the multi-scale, just to show you that things are not so hard, but not so obvious in some ways. Suppose you have a potential operator. In other words, suppose I have potential charges on the spiral here. Okay, so my matrix is coming. Each one of the points on the spiral is a point yi. Each one of the points out here on this surface is a point xj, and I have a matrix 1 over xi minus yj. Okay, so it's a potential, electrostatic potential of a point here measured here, or the potential of a point here measured here. So now I'm getting to physics. Okay, that's my matrix, and somebody just put it down there. Okay, in any case, when you write a two-dimensional structure on a matrix, you have to have a space-filling curve. It's a complete garbage. So writing the matrix is garbage. Okay, the geometry is not. Usually, when you want to analyze this is done by multi-scale analysis. You're saying, well, if I look at if I want to understand the potential here. On here, I have to organize, I can develop this matrix in some sort of product of Haar or a wavelet basis. And what I'm really telling you is a multi-scale analysis on the rows is this one. This is one scale, this is another scale. The multi-scale analysis on the columns will be the one that you're seeing here. Okay, so this thing's, it's not abstract. It's something that people have been doing for the last 50 years, right? It tells you how you organize the impact of the matrix, how a blob here would affect a blob here, and it will give you also a fast algorithm, just converting that matrix in this dual basis that I have, one basis on the spiral, the other one here, will give you an algorithm completely competitive with sort of the best FMM algorithm in some sense, in this case. And I've done just data analysis. So let's just one word about how the hierarchy was actually obtained. So actually maybe I should go this. So the basic fundamental idea is this, and maybe I'll back up again. if you have points in Rn, and n is large, like in this case the 2 points are those 2 images, okay, to measure the similarity between images as being in terms of the distance between them is completely idiotic, okay, because, or in terms of the dot product between them. Let's say in terms of how, take the dot product between this vector, so every pixel is one coordinate, right? Take the dot product between this and that, just counts how many pixels they have in common. It's just 1 here relative to the total number. The dot products, they're basically orthogonal, okay? So in high dimension, measuring relationship between vectors by using dot products is a completely useless exercise unless you look at points which are really close to each other, okay? So in other words, you can infer, if I had another one which was almost identical, I could infer that the two should be linked together. They're basically the same object. So I need to build a geometry in Rn when I have this data in which I really only compare things which are really close to each other. Let's say I had 2 people with 2 profiles. I would link those 2 people as being of the same kind if, say, 90% or 99% of the responses are identical. And otherwise, I ignore the issue. Okay, so this allows me to build a graph on the population or a graph on the questions. When you build that graph, you can view this as like building a manifold. You can build a metric or a geometry. Normally, geometers will do a geodesic metric, but in a data sense, it makes no sense. So you do a diffusion metric, which measures the preponderance of linkages between points. The remarkable thing is that you can embed it in Euclidean space so that Euclidean distance is measuring preponderance of linkages, and that allows you to build those hierarchies on the columns, hierarchies on the rows. Adding more coordinates allows you to improve your hierarchies, denoise them, and do things. But at the end, once you have the underlying structure, the harmonic analysis is identical. And I think there are some references in this thing which you will have access to, which describe most of those things, including another lecture I gave 2 or 3 years ago on this, and you'll hear a little bit more from Mauro tomorrow about related geometries as they come about. But the point is that to do analysis, first you build the underlying geometry, you build the underlying operators. The analysis of functions is the analysis of the operators on the underlying geometry. And you use them both to do that. This has been a long story going back. I think it has a traditions of at least 100 years in mathematics, that geometry is very difficult. On the other hand, understanding operators on the structure is a little bit easier, and we have heard a little bit of that before. So comparing operators is a good way of comparing geometries. So people have compared differential manifolds to each other by looking at comparing the Laplacian, comparing the diffusions, or doing things of that sort, or comparing Dirac operators. This is a long tradition. Same thing is happening here. Our geometries are all discrete because they are large clouds of points, but between a large cloud of points and a continuous version, you know, it's really analysis. It's not combinatorics anymore. Of course, you don't trust any tree you build, right? You always get the joint conclusion of a whole array of trees. Okay. No, that's not true. So the tree is not subjective it's subjective in one way and not subjective in another way. Okay. The lack of subjectivity comes from the fact that you are only linking things that you know for sure should be linked. Okay. So with some high probability. The subjective part, where there is a stochastic choice made, is where I take the whole population and break it into groups which are disjoint, okay, which are very tight groups, okay, And there are many ways of doing that, right? So that's a stochastic process, right? And so that would be level 1 of my tree, okay? Then I group those groups together. That's another stochastic thing. That's level 2 of my tree, okay? So it's like when you do the binary tree on 0, 1. It's an arbitrary tree. You can shift it by an epsilon, you get another one, right? So you don't trust, the binary tree doesn't give you a holder or anything, but the combination of them does, okay?
I mean, when you have the eigenvectors matrix, there is one.
Oh yeah, but there you have everything is known, okay? So there, let's say you look at eigenvectors on a perturbation of the sphere, right? Or if spherical harmonics, you can cheat, right? But suppose you have a bump on the sphere, okay? And you look at the eigenvectors of Laplacian relative to that. Doing a multi-scale partitioning of that manifold is very easy because you do it by patching. And then you relate eigenvectors to each other by how they relate globally and also how they relate to each other on the different subsets at different scales, okay? So this is pure geometry. There's nothing. Okay, the choice of the subsets is there will be boundary issues, but then you can wash it out. Right? You can take a nice partition of unity. You can do all kinds of things.
I was in the other room, so
yeah.
There is something that actually what you're telling us is this is sort of forget the probabilistic approach. This is like a deterministic PCA.
It's not deterministic completely. It's a local PCA. Okay. First of all, it's not a PCA. It's not a PCA. But say if you wanted to, you could build things like this, but you have to do a local PCA. The assumption is that in different regions of the data, you need a different PCA. Right. I'll give you an example. Okay. Mara will talk about it tomorrow, but I'll give you another example, which is. Precedes all of that. You have a set of all documents in the universe, right? And usually you organize documents by the vocabulary being used in them. So people do a PCA on all the documents, all the vocabularies. You get, and the coordinates in that are latent semantic coordinates. So the coordinates for the whole universe are garbage. When you're dealing with, say, political documents or cooking documents, you want other coordinates, right? The role of different words in those and the meaning of the words changes from context to context.
Yeah, that's true. But because you put, if you put random variables that are not naturally correlated, we have an educated case that are not correlated, like the words being used in a political document, the words being used in a cooking book. There should be some.
Right, but you see. Yes or no?
That should be reflected in the data.
Yes or no? Look, you say the word win, right? You see it in sports, and you see it in politics, and you see it there. You see it all over the place, but it has a slightly different meaning, right? I mean, you saw Jeopardy the other day, right? And the point is, all the meaning is contextual, okay? What this was showing you is some way of organizing the coordinates relative to the context and defining the coordinates, defining sort of meta-coordinates or bag of words, if you wish, right, related to context.
Particular context of responders and inputs.
Right.
Because then somebody else comes or 10 more come that I didn't interview before.
That's okay.
Things changes completely.
Not really.
You can use it for prediction.
You can use it incredibly for prediction. In fact, in this questionnaire, you can throw away half the responses and you can fill them back in very easily. And
that could possibly happen because we have a very big sample, but then the question is how big the sample is. So the theory doesn't take that into account.
It does. It does. Because the theory allows you to do the following thing. You take the data and you go through this process. Then there is going to be a piece of the data which is consistent and a piece of the data which is not consistent. This is what I described as decomposition. The one that's not consistent, okay, which you can measure at every individual data point, you pull it out. It may need a completely different model, okay, with a different geometry. Okay, you give me a garbage matrix like random 0 1s in both variables, I won't be able to do anything with it. Okay. So the point is you have a way of measuring, have I done something useful on a piece of the data or not? If I have done something useful, I pull it out. Okay. If I haven't, I don't do anything.
We have another question in the back.
On the announcement slide which you showed us, there was a question at the bottom relating to the dimension, the sort of intrinsic dimension of the set of data when doing dimensional reduction. And I'm not sure if I missed something, but did you say you had a partial answer to that which you now just skipped, or I guess this must be a major open question?
It's not a major open question. I mean, you'll hear Maura talk about it tomorrow morning. I mean, you're assuming there is a dimension, right? I mean, maybe it's a fractal dimension. Okay. I mean, I'm not assuming it's a manifold or anything. I'm just assuming this is stochastic data that you got, right? You could put all kind of underlying models. You can assume the data is around some manifold. You can assume the data is generated by some stochastic differential system, right? Or you can assume nothing, see if you can do anything useful in terms of compressing the data, which is what I was describing, right? By just shuffling the rows and columns and building a geometry and getting the ability to do predictions. And then I decide, yes, if I did something useful, great, I'll pull it out and look at the part where I failed and maybe start all over, right?
Does it have an impression that in practice this dimensional reduction is often done in a quite naive way?
Well, you'll hear about it tomorrow. It's not naive.
You mentioned about the student and the Bible study.
Yes, I can tell you the story if you have 2 minutes, okay? The question was the following. I wanted him to do something very simple, which is to take one document, one book. It could be a book in neurology, translated by somebody to Chinese, okay? And look at the index of the same book in English, look at the index of the book in Chinese. Then, since it's the same book, I should be able to very easily match, and I know the list, the paragraphs are known, those coordinates are known. I can should be easily match the words, and so it was a way of maybe getting a sort of a lexicon, if you wish, or a dictionary for special languages, right? It could be a dialect, could be a professional dialect, it doesn't matter. So, by misluck or luck, he couldn't find a book. So which had universal coordinates, okay, which was translated in many languages. So he found the Bible because it's translated in every language, and coordinates, the verses are universal coordinates, right? But every Bible is a different political document, okay, because the translation is done by somebody who has an agenda, okay, and so the issue was, all right, so the question is, all right, so I'll look, so I have all those sub-documents of the Bible, which are my, if you wish, which are pages or a group of verses or something, and then I have the vocabularies in the different languages. So what happened there is we decided we need to organize the Bible into contextual groups, right? In other words, verses we deal with the same topic and so on. So we looked at all languages together, okay? So this was as basically all of the language. We had 3 languages, so it was French, English, and German. We put them all together as coordinates of each one of the paragraphs, and we use that to initially organize the contextual coordinates, and then we looked at all languages as sort of a universal language, and basically for each word we related to words if they appeared in the same verses, in the same context, in the same meta context, and so on, just like what I was describing. And now you got to the meaning of the words in some sense, right? Because the context is define the meaning. It became completely obvious that some words have different meanings in different books because they're really used differently. Like water is sometimes used for drinking and sometimes for a purification, right? Which is a religious concept. And so you saw that popping out, but in order for this, so this thing did not work at all initially. You needed to do this iteration back and forth from context to concept at least 6 times until it completely stabilized. And then you started to get some real meaning. And so what you got is for any given word, you could say, is the word being used consistently So we got a sort of, I would say, an agnostic Bible, again, no pun intended, okay, in which you take the universal understanding of the different translations of a given word. You could also do it, build a dictionary now, because every word in this graph of all languages, if you had the nearest neighbor, if you had two mutual nearest neighbors in that, they were translations. One was in German, one was in English, they were translations. And languages are really different. I mean, the word home, for example, does not have an equivalent in French. I mean, it has the equivalent as house, but house is not home. Right? And things like that. So there was a need to do this thing back and forth, and we were really forced to this algorithm. And then we started to understand we could do it everywhere. That's really how you should do things, or how you could do things.
Okay, let's send the speaker now, and let's continue discussions. Just a few announcements. At 5 o'clock now we have the post